In this video, we're going to introduce something called a Noetherian domain, and that's going to be useful for our discussion later on of unique prime factorization. Here's a definition. Let R be an integral domain. We say R is Noetherian if every infinite ascending chain of ideals of R eventually stabilizes. So here's what that means. That is, if I0, I1, and I2, and so on, all of these are ideals. If this is an infinite ascending chain of ideals of R, that is, each I sub j is an ideal of R for all j in the natural numbers, including 0, then there exists some n, a natural number, such that I sub j is equal to I sub n for all j greater than or equal to n. So in other words, being a Noetherian domain means that I cannot set up an infinite ascending chain of ideals where this one is strictly a subset of this one, is a proper subset of this one, and so on, where each one is a proper subset of the next and the chain goes on forever. You cannot do that. You may wonder why in the world we would care about this, but we're actually going to find this is an extremely useful tool for proving that something is a unique factorization domain later on. We'll need other conditions. We'll need, for example, the fact that we have a principal ideal domain to do that. We need more than just the fact that we have a Noetherian domain. But we're actually going to prove that every principal ideal is Noetherian. But for now, I just want to give one example that doesn't require doing quite as much work. So let's suppose we're thinking about the domain of the integers. That's an integral domain, and we will prove that this is Noetherian. All right, so suppose I have a chain of ideals. And by the way, I'm using the less than or equal to sign because often we do that when we're talking about ideals rather than just random subsets. But you could use the subset symbol as well. There'd be nothing wrong with that. So suppose this is a chain of ideals of Z. Okay, before going on with the proof, I just want to think about why this might be true, why we might not be able to assemble an infinite, strictly ascending chain of ideals in the integers. So one thing that we know is that in the integers, every ideal is principal. So for example, maybe this is something like, I don't know, the ideal generated by 24. Okay, so every ideal in the chain after that has to be something that contains all of the multiples of 24. So for example, this ideal here, I1, could not be the ideal generated by 5. That does not contain 24. So whatever I put next in the chain has to be something that as an ideal is bigger. So maybe the ideal generated by 8. Could be the ideal generated by 24 as well, but I'm going to go ahead and make this efficient by pulling out all of the repetitions from the chain. Okay, now, first of all, I should address something. It probably looks weird to write brackets 24 is less than or equal to brackets 8, but that's because this contains all multiples of 8, and that includes all multiples of 24. So this actually is the bigger ideal in terms of elements included in it. All right, so for my next ideal, I might select something that contains all of the multiples of 8, like maybe all the multiples of 4, and then maybe after that I have all of the multiples of 2, but then after that I kind of get boxed in. I don't really have a lot of other places to go. I could make the next ideal the ideal generated by 1, but then there's really no place else to go. At that point, the ideal chain has to stabilize. Now, that's not to say that the chain has to set up exactly this way. I made a choice here, and really I made a choice at every step along the way. But I think the one thing you'll notice here is that assuming that we don't have any repeats in the chain, then at some point we're going to have to go down in terms of the generator. The generator is going to have to be something less than what generated the previous ideal. And that generator keeps having to go down. And because we have a well-ordering principle for natural numbers, and every ideal is generated by either a natural number, a positive natural number, or 0, eventually we just don't have any place else to go. Eventually either we end up at 1 or we end up at someplace else, and we don't want to go any bigger than that in terms of the ideals. So that's how the proof is going to work, is we know that every ideal is generated either by 0 or by a positive integer. And if we have ideals generated by 0, that's just going to be boring after a while. And if we have ideals generated by positive integers, then eventually we have to stop. We have to stop getting bigger. So anyway, back to the proof. Let me just close that off. Okay, so that was an example. All right, so back to the proof. If no ideal in the chain contains positive integers, then, well, every ideal has to be 0. That is, I sub j is equal to the trivial ideal for all j in the natural numbers. Okay, so then I can just take my n to be 0, and my I sub n is the ideal generated by 0, and that's where the chain stabilizes. Okay, so no problem there. So the only case left to address is what happens if some ideal in the chain does contain positive integers. Now, first of all, if some ideal in the chain has positive integers, then every chain after that has to have positive integers because these ideals are ascending. Each one is included in the next. So all subsequent ideals must as well. And each such ideal is generated by some positive integer aj, so that ij is equal to the ideal generated by aj, where aj is positive, for each such j. So we're allowing for the fact that there may still be 0 ideals in the chain, but eventually we have to get off of 0, otherwise we have stabilized. Okay, so after a certain point, every ideal in the chain is generated by some positive integer, and we're going to index those. We're going to call those a sub j. But now they're positive integers, and there's a non-empty collection of them. That means that by well ordering, we can let n be a natural number such that a sub n is the smallest of the aj's. And once we do that, well, we know that since I sub n, or sorry, let's say I sub j is included in I sub j plus 1 for every j, we have that, and I'm just translating into the principal ideal notation. This is a subset of aj plus 1 for all j. And so, one thing that results from that is that a sub j has to be in this ideal. A sub j is in the ideal a sub j plus 1 for all such j. When I say all such j, I mean all the j's for which a sub j is positive. Okay, and so that means that a sub j plus 1 divides a sub j for all such j. Sorry, this all such j I know is getting old. I don't have a better way of saying it. Okay, but this means that for all j greater than or equal to n, a sub j is going to have to divide a sub n, because what this step here shows is that each subsequent generator has to divide the one before it. So if I have a sub n, and that's my minimal generator, then every subsequent generator has to divide it. And these are all positive. So that also means A sub j has to be less than or equal to A sub n for all j greater than or equal to n. Okay, but now we have an issue because we also know that we set A sub n to be the minimal among all of the A sub j's. A sub n is the smallest. So now that means, since A sub n is minimal, it is also true that A sub n is less than or equal to all the A sub j's, such that A sub j is positive. Okay, so given this, and given this, this means, so this condition, by the way, held only when j is greater than or equal to n. So all this means that A sub j has to equal A sub n for all j greater than or equal to n. And so now we are in a perfect position to prove that this chain stabilizes. So ideal generated by A sub n is equal to the ideal generated by A sub n plus 1 is equal to the ideal generated by A sub n plus 2, etc. That is, I sub j is equal to I sub n for all j greater than or equal to n. And then we're done. Therefore, every infinite chain of ideals, every infinite ascending chain stabilizes. And that means Z is a Noetherian domain. And just one quick note before we wrap up. So what we did in this video was we showed one example of a Noetherian domain. We didn't prove anything general like what we're going to prove later, which is that every principal ideal domain is Noetherian. But that's not what we did here. And in fact, the strategy for that proof requires a little bit more use of ring theory than what we did here. But I wanted to say before we quit, in case you've never seen this name before, this is named after a mathematician named Emmy Noether, who is considered by many to be the mother of modern algebra. She invented the use of chain conditions like these to analyze properties of rings. So we will see this a little bit more in this course, but if you take other courses in commutative algebra, you're likely to see a lot of Noetherian things.